Good morning everyone. My name is Krisha Mange and today in this reflection video I will be sharing my learning journey on the topic data structure and algorithm using Java. In the world of computer science, data is everywhere. Every application we use, whether it is search engine, social media platform, online shopping website or banking system, processes huge amounts of data every second. While exploring this topic, I realized that simply storing the data is not enough. The way we organize and process the data efficiently is what really determines the performance of a system. This is where the data structure and algorithm becomes extremely important. Through this learning journey, I explored several fundamental concepts such as array, linked list, stack, queue, trees, graphs, and algorithm efficiency. Understanding these concepts helped me see how programmers design systems that can store, retrieve, and process the information efficiently. Why data structure matters? One of the first questions I asked while studying this topic was why data structures are so important. Data structure help organize data in a way that makes it easier and faster to access, modify, and process. For example, imagine a library with thousands of books. If the books were placed randomly, it would be extremely difficult to find a specific book. However, libraries organize the books using categories, shelves, and indexing system so that the books can be found quickly. In the same way, data structures organize the data inside computer system. For example, when we search for a contact in our smartphone, the system must quickly find the correct name among hundreds or thousands of contacts. Efficient data structure help makes this process faster and efficient. This made me realize that the performance of many software systems depends heavily on the choice of the data structure. Now, what are algorithms? After understanding the data structure, the next important concept I explored was algorithm. An algorithm is simply a step-by-step procedure used to solve a problem or perform a task. For example, when we follow a recipe to cook a meal, we follow a sequence of steps. In a similar way, computers follow algorithm to process the data and solve the problem. Search engines like Google use complex algorithms to find the most relevant results among billions of web pages. Even simple tasks like sorting numbers, searching for data, or processing the transactions rely on the algorithm. Learning about algorithm helped me understand that the data structure and algorithm work together to solve computational problems efficiently. Arrays. Now we will be seeing the arrays, one of the simplest and most commonly used data structures. An array stores multiple elements in contiguous memory location, allowing the computer to access them quickly using an index. For example, if we have an array storing student marks, we can easily access the marks of a specific student using its index number. A real life example of an array is a row of locker in a school. Each locker has a number, and you can directly open that locker if you know its number. Arrays are very efficient when we need fast access to the elements, but they have limitations because their size is usually fixed. While learning about arrays, I understood how they form the foundation for many other complex data structures. Now we will see what is linked list. Unlike arrays, linked lists do not store elements in a contiguous memory location. Instead, each element in a linked list contains two parts, the data and the reference to the next element in the list. This structure allows linked lists to grow or shrink dynamically. A good real-life example of a linked list is a train with multiple coaches. Each coach is connected to the next one, forming a chain. If a new coach needs to be added, it can simply be attached to the train without reorganizing the entire structure. This flexibility makes linked list useful in applications where data frequently changes or needs to instead or removed. Next is the stack structure. A stack follows the principles of LIFO, that is last in, first out. This means the last element added to the stack is the first one to be removed. A simple real life example of a stack is a pile of plates in a cafeteria. The last plate placed on top is the first one to be taken. Stacks are used in many computing applications. For example, they are used in undo operations in text editors. When you press undo, the program reverses the most recent action first. They are also used in function calls in programming languages where the most common recent function call is processed first. Learning about stacks helped me understand how systems manage tasks and operations efficiently. Another important data structure is the queue, which works differently from a stack. A queue follows the principles of first in, first out, also known as FIFO. This means the first element added to the queue is the first one to be removed. A common real life example is a line at a ticket counter or a supermarket checkout where the person who arrives first gets served first. Queues are widely used in computer systems. For example, operating system uses queues to manage the processes waiting for the CPU execution. Similarly, printers use queues to manage multiple print requests. Understanding queries, understanding queues helped me see how systems handle tasks in an organized and fair manner. Trees and graph. As I continued learning, I discovered more advanced data structures such as trees and graphs. A tree structure organizes data hierarchically with a root node and multiple child nodes. A common example of a tree structure is a company's organizational hierarchy, where a CEO is at the top, followed by the managers and the employees. Trees are widely used in databases, file system, and search algorithms. Graphs, on the other hand, represent the relationship between the different entities. For example, social media platforms use graph structure to represent connections between the user. Navigation systems like Google Maps also use graph algorithm to calculate the shortest path between two locations. Learning about trees and graphs helped me understand how complex systems manage large network of interconnected data. Now we will see the algorithm efficiency. Not all the algorithms perform tasks with the same speed or efficiency. Some algorithms take much longer time to process the data, especially when the amount of data increases. To measure this efficiency, programmers use concepts such as time complexity and big O notation. For example, if we need to search for a number in a list, simple search might check every element one by one. However, more advanced algorithms like binary search can find the element much faster by repeatedly dividing the list into helps. Understanding algorithm efficiency helped me realize that choosing the right algorithm is extremely important when designing the software systems. So to conclude, this learning activity helped me understand the fundamental role of data structures and algorithm in computer science. Before studying this topic, I mainly focused on writing programs. But now I realize that the efficiency of a program depends greatly on how the data is organized and processed. From arrays and linked list to stacks, queues, trees, and graph. Each data structure serves a specific purpose in solving different computational algorithms. This learning journey helped me see how these concepts are used in real world systems such as search engine, social media platforms, navigation system, and operating system. Overall, this experience improved my understanding of how efficient software systems are designed and strengthened my interest in learning more about advanced algorithms and data structures in the future. Thank you.